Chapter 5 Preflight and Ground Operations Introduction. Preflight preparation should include the overall evaluation of the pilot, experience, sleep, food and water, drugs or medications, stress, illness, aircraft, certificate/documents, airworthiness, fuel, weight does not exceed maximum, performance requirements, equipment, environment, weather conditions, density, altitude, forecast for departure and destination airfields, route of flight, runway lengths, external pressures, schedules, available alternatives, purpose of flight, often remembered as PAVE. It is important to consider each of these factors and establish personal minimums for ying. Where to fly. The weight shift control, WSC aircraft can be transported by trailer from one ying file to the next. For as many benefits as this provides, transporting the aircraft into unfamiliar territory also includes some safety and operational issues. Contact airport management to inquire about any special arrangements to be made prior to arriving by trailer, Figure 5.1, and there may be special considerations for ying WSC aircraft with other aircraft. With smaller patterns typically used by WSC aircraft, as covered in Chapter 10, Airport Traffic patterns, airport management may want a pilot to operate over sparsely populated areas rather than the normal airplane patterns over congested areas because of the unique noise of the WSC aircraft. Figure 5.2, check the airport/facility directory, A/FD, all required airport information per Title 14 of the Code of Federal Regulations, 14 CFR, Part 91 Section 103, Preflight information. Some operation examples are Traffic pattern information, noise abatement procedures, no FLY zones surrounding the airport, and special accommodations that may need to be arranged for WSC aircraft. Because of the wide range of flying characteristics of the WSC aircraft, inform local pilots about some of the incidentals of the specific WSC aircraft, for example, ying low and slow for certain configurations. The more non-WSC aircraft pilots know about WSC flight characteristics and intentions, the better they understand how to cooperate in flight. Sharing the same airspace with various aircraft categories requires pilots to know and understand the rules and understand the flight characteristics and performance limitations of the different aircraft. For operations at non-aircraft fields, special considerations must be evaluated. Permission is necessary to use private property as an airstrip. Locate the area on an aeronautical sectional chart to check for possible airspace violations or unusual hazards that could arise by not knowing the terrain or location. Avoid loitering around residential structures and animal enclosures because of the slow flight characteristics of WSC aircraft and distinct engine noise. While selecting a takeoff position, make certain the approach and takeoff paths are clear of other aircraft. Fences, power lines, trees, buildings, and other obstacles should not be in the immediate flight path unless the pilot is certain he or she is able to safely clear them during takeoff and landing operations. Walk the entire length of the intended takeoff and landing area prior to departure. Figure 5.3, look for holes, muddy spots, rocks, dips in the terrain, high grass, and other objects that can cause problems during takeoff and landing. Physically mark areas of concern with paint, flags, or cones. Uneven ground, mud, potholes, or items in fields such as rocks might not be visible from the air. Plowed rows and vegetation are larger than they appear from the air. Unfamiliar fields can make suitable landing areas for emergencies, but should not be used as intended landing areas. Extreme caution must be exercised when operating from a new field or area for the first time. Pre-flight actions. A pilot must become familiar with all available information concerning the flight, including runway lengths at airport of intended use, takeoff and landing distance accounting for airport elevation and runway slope, aircraft gross weight, wind, and temperature. For a cross-country flight not in the vicinity of the takeoff/departure airport, information must include weather reports and forecasts, fuel requirements, and alternatives available if the planned flight cannot be completed. Weather is a determining factor for all flight operations. Before any flight is considered, pilots should obtain regional and local information to first determine if the predicted weather for the planned flight is safe. Regional weather. Understanding the overall weather in the region being flown provides an overview of conditions and how they can change during flight. Fronts, pressure systems, isobars, and the jet stream determine the weather. There are a number of information resources from which to find the regional view of weather systems, observed and predicted. Surface analysis charts show these regional systems, which are common on weather internet sites and TV broadcasts. Figure 5.4. Review the pilot's Handbook of Aeronautical Knowledge for a comprehensive understanding of weather theory, reports, forecasts, and charts for weather concepts covered throughout this weather section. There are many sources for obtaining a weather brief ENG, such as www.aviationweather.gov, www.nws.noaa.gov, 1-800-WX brief, and a variety of internet sites that specialize in local and regional weather. Local conditions in gathering weather information for a flight. Obtain current and forecast conditions where ying, as well as alternate airports in case landing at the intended destination is not possible. These conditions should include wind, surface and winds aloft, moisture, stability, and pressure. Surface wind predictions and observations can be looked at with a number of internet resources. The National Weather Aviation Service provides observations, meter, and forecasts, TAF, for areas with weather reporting capabilities. Winds aloft are forecast winds at higher altitudes than the surface for locations throughout the United States. Refer to the Pilot's Handbook of Aeronautical Knowledge for an understanding of the winds and temperatures aloft tables. Winds aloft, too, are important for flight planning and safety. A typical situation during morning hours is cold air from the night settling, creating calm winds at the surface with the winds aloft, 300 to 3,000 feet, at 30 knots. As the surface begins to warm from the sun, the cold surface air starts to warm and rise, allowing the high winds from above to mix and lower to the surface. The wind shear area in between the high winds above and calm winds below is usually turbulent and can overwhelm aircraft or pilot capabilities. Therefore, it is a dangerous practice to look only at the windsock for surface winds when there could be strong winds above. Winds aloft must be evaluated for safe flight. Figure 5.5, during initial solo flights, the wind should be relatively calm to fly safely. As experience is gained, pilot wind limitations can be increased. It is not until the pilot has had dual training in crosswinds, bumpy conditions, and signify can't pilot in command, PIC, time soloing in mild conditions that pilot wind conditions should approach the aircraft limitations. A safe pilot understands aircraft and personal limitations. Moisture in the air has a signify can effect on weather. If the relative humidity is high, the chance of clouds forming at lower altitudes is more likely. Clouds forming at lower altitudes create visibility problems that can create instrument meteorological conditions, IMC, in which the visibility is below that required for safe flight. The temperature dew point spread is the basis for determining at what altitude moisture condenses and clouds form. It is important to be particularly watchful for low visibilities when the air and dew point temperatures are within a spread of 3 to 4 degrees. The closer these temperatures are to each other, the greater the chance for fog or clouds forming with reduced visibility conditions. Consider a scenario where the destination airport currently has a temperature dew point spread of 4 degrees Fahrenheit, and it is evening when the atmosphere is cooling down. Since the temperature dew point convergence rate is 4.4 degrees for every 1,000 feet, the cloud/ceiling would be about 1,000 feet above ground level AGL. Since it is cooling down, the temperature dew point spread is decreasing, lowering the cloud level. Therefore, the 1,000-foot AGL ceiling is lowering, creating IMC conditions that are not safe. For this scenario, the flight should not be attempted. Air temperature and humidity directly affect the performance of the WSC wing and engine. The higher the temperature, humidity, and actual altitude of the operating faa-h-8083-5, the greater role density altitude plays in determining how much runway the WSC aircraft needs to get off the ground with the load on board, and how much climb performance is required once airborne. The WSC aircraft may have cleared the obstacle at 8 a.m. when the weather conditions were cooler with less humidity. At 1 p.m. with increased air temperature and higher humidity levels, the pilot must re-evaluate the performance of that same aircraft. A full understanding of density altitude is necessary to be a safe WSC pilot. Refer to the Pilot's Handbook of Aeronautical Knowledge for density altitude and weight effects on performance. The rate of temperature decrease with increased altitude determines the stability of the air. The stability of the air determines the vertical air currents that develop during the day as the area is heated by the sun. These rising vertical air currents are commonly known as thermals. Generally, stable air has mild thermals and therefore less turbulence than unstable air. Unstable air rises faster, creating greater turbulence. Highly unstable air rises rapidly and, with enough moisture, can build into thunderstorms. Air stability is easily determined by the rate at which the temperature drops with increased altitude. A standard atmosphere is where the temperature drops 2 degrees Celsius for every 1,000 foot increase. If the temperature drops less than 2 degrees Celsius per 1,000 feet, the air is more stable with less vertical wind thermals developed during the day. If the temperature drops more than 2 degrees Celsius per 1,000 feet, the air is more unstable with more powerful vertical air currents developed during the day, creating greater turbulence. In addition to air stability, barometric pressure has a large effect on weather. Low pressure in the area, below the standard atmosphere of 29.92 Hg, is generally rising air with dynamic and unsettled weather. High pressure above the standard atmosphere in the area is generally sinking air, resulting in good weather for ying. Many airports have automated weather systems in which pilots can call the automated weather sensor platforms that collect weather data at airports and listen to this information via radio and/or landline. Radio frequencies are on the sectional chart, and the A/FD has the telephone numbers for these stations. The systems currently available are the Automated Surface Observing System, ASOS, Automated Weather Sensor System, AWSS, and Automated Weather Observation System, AWOS. Local conditions of wind, moisture, stability, and barometric pressure are factors that should be researched before ight to make a competent decision of go or no go to fly. High winds and moist, unstable air with a low barometric pressure indicate undesirable ying conditions. Light winds and dry, stable air with high pressure indicate favorable ying conditions. Pilots should research and document these local conditions before ight to predict the ying conditions and compare the actual ying conditions to the predictions to learn and develop knowledge from the information resources available for ight. In addition to weather, the national airspace needs to be checked to ensure there are no temporary flight restrictions, TFR, for the locations planned to fly. TFRs may be found at www.tfr.fa.gov/. For a complete pre-flight brief ENG of weather and TFRs, call 1-800-WX-BRIEF. Clouds visually tell what the air is doing, which provides valuable information for any flight. To understand the different cloud formations and the ground/air effects produced, refer to weather theory in the Pilot's Handbook of Aeronautical Knowledge. Figure 5.6, cloud clearance and visibility should be maintained for the operations intended to be conducted. The chapter covering the National Airspace System, NAS, provides cloud clearance requirements in each class of airspace. A pilot should not fly when ground and flight visibility are below minimums for his or her pilot certificate and the class of airspace where operating. Knowledge of mechanical turbulence and how to determine where it can occur is also important. The lee side of objects can feel turbulence from the wind up to 10 times the height of the object. The stronger the wind is, the stronger the turbulence is. Figures 5-7 and 5-8, in addition to adhering to the regulations and manufacturer recommendations for weather conditions, it is important to develop a set of personal minimums such as wind limitations, time of day, and temperature dew point spread. These minimums will evolve as a pilot gains experience and are also dependent on recency and currency in the make/model of aircraft being flown. Weight and loading must be considered before each flight. Do not exceed the maximum gross weight as specified in the Pilot's Operating Handbook, POH. The balance of the pilot, passenger, fuel, and baggage is usually not an issue, but must be reviewed in the PO for the specific make/model since some may have balance limitations. The fore and aft carriage attachment to the wing hang point must be within the limits as specified in the PO for weight and loading of the carriage. Always follow the PO performance limitations. Transporting it is best to keep the WSC aircraft in an enclosed hangar, but trailers may be used to transport, store, and retrieve the WSC carriage. If the trailer is large enough, the wing can also faa-t inside the trailer. If not, then it must faa-t on top of a trailer, truck, or recreational vehicle, RV. Figure 5.9, enclosed trailers are preferred so the carriage is protected from the outside elements such as dust, rain, mud, road debris, and the interested person who may want to tinker with the carriage. The WSC carriage should faa-t snugly without being forced, be guarded against Trafฝี, and well secured within any trailer. It is best to utilize hard points on the carriage frame and secure each wheel so the carriage cannot move fore and aft during transport. This is best accomplished by faa-h-8083-5 tying the front wheel from the axles, the fork, or a hard point on the frame with a slight forward pull. Then, secure the rear wheels from the axles or a hard point on the frame with a slight rearward pull. Guides on the side of the wheels and wheel chocks in front and back of each wheel are additionally helpful to secure the carriage on any trailer. The wing must have ample padding and should have at least 3 support points where it rests for transport. Transporting the wing properly is of critical importance because the wing resting on any hard surface can wear a hole in the sail and cause structural damage to the tubing. The greatest wear and tear on a wing can occur during transportation. Each support point should have equal pressure, no single point taking most of the load. The wing should be tied down at each attachment point to secure it, but not tight enough to damage the wing. Wide straps are better than thin ropes because the greater width creates less concentrated pressure on the wing at each tie-down point. Once the loading of the carriage and wing is complete, Figure 5.9, take a short drive, stop, and check for rubbing or Trafฟี่of components. Prior to taking the tow vehicle and trailer on the road, inspect the tires for proper inflation and adequate tread. Ensure all lights are operable, the hitch is free-moving and well lubricated, the tow vehicle attachment is rated for the weight of the trailer, and the vehicle and trailer brakes are operable. Avoid towing with too much or too little tongue weight, which causes the trailer to fishtail at certain speeds, possibly rendering it uncontrollable. Be extremely cautious when unloading the wing and carriage. This is best done with 2 people since the wing usually weighs more than 100 pounds, Figure 5.10, and the carriage usually must roll down some incline to get from the trailer to the ground. Some carriages may be tail heavy without the wing, and caution must be exercised, especially moving up and down ramps. Check propeller clearance on the ground when transitioning onto or off of a ramp and propeller clearance going into and out of an enclosed trailer. If the carriage is transported in an open trailer, it should be covered and the propeller secured so it does not rotate/windmill during transport. Setting up the WSC aircraft, find a suitable area to set up the wing, such as grass, cement, or pavement out of the wind. Inside a large hangar is preferable since wind gusts are not a problem. If setting up outside, align the wing perpendicular to the wind. Most wings set up with the same basic procedure shown in figures 5 to 11 through 5 to 33, but the PO should be referenced for the specific WSC aircraft. Rotate the wing bag so the zipper is facing up. Figure 5.11, unzip the bag. When setting up the wing, pay close attention to the specific pads, where they are located, and how they are attached for each component of the wing. As shown in figure 5.12, the padding is made specifically for the control frame between the down tubes and the control bar. If every pad is not utilized when taking it down and transporting there, any wing, it is a good idea to take pictures, draw sketches, or take notes regarding protective pad location so they can be put back in the proper location during takedown. Assemble the triangular control frame without attaching the wires to the nose. Figure 5.13, rotate the wing up onto its control frame. Figure 5.14, place the front wires near the control bar so no one walks on them, remove, and roll up the cover bag. Figure 5.15, release the wing tie straps that are holding the leading edges together. Figure 5.16, spread the wing slightly. Remove the pads from the wing keel and king post. Note the protective pads still on the wing tips, protecting them from the ground during most of the wing setup procedure. Figure 5.17, continually manage the wing pads and wing tie straps by rolling the pads into the cover bag so they do not blow away. Figure 5.18, if the king post is loose, insert it onto the keel to stand upright. If the king post is attached, swing it upright. Topless wings have no king post. Spread the wings as necessary to keep the king post straight up, Figure 5.19, spreading them out carefully and evenly. Do not force anything. Ensure the wires are not wrapped around anything. Separate the right and left battens. Separate the straight battens, for a double surface wing, and set them to the side. Lay out the battens, longest to shortest from the root to the tip next to the pocket they go into on both sides. Note the protective pads are still on the wing tips so they are protected. Figure 5.20, insert the battens into the batten pockets, starting at the root and work out to the tip. Figure 5.21, most batten attachments are double pull. Figure 5.22, some manufacturers use cord or elastic, and others use a system that slips into the sail itself. See the PO for wing details. Insert battens from the root towards the tip about 3/4 the way out on each side. Leave the tip battens for later. Spread the wings as far as possible. Figure 5.23, check to ensure all the wires are straight, not wrapped around, and clear to tension the wing. Tension the wing by pulling back on the crossbar tensioning cable and pulling the crossbar back into position. This may require significant effort for some wings. Secure the tensioning cable to the back of the keel. Figure 5.24, if the keel does not extend out, then support the aft end of the keel to lift the tips off of the ground. Figure 5.25, move to the front and secure the front control frame ying wires to the underside nose attachment. Figure 5.26, remove the tip bag protectors and install the tip battens, continuing to move from the root to the tips on each side. Insert the washout strut into the leading edge. Each manufacturer has its own washout strut systems and tip battens. Some manufacturers have no washout struts. Refer to the PO for wing specifics. Figure 5.27. Insert bottom battens for a double surface. If inside a hangar where there is no wind, this can be done by putting the nose down, making it easier to install the lower battens. Figure 5.28, if not already accomplished, Lift up on the back of the keel and put the wing on its nose. Lower the undercarriage mast and line up the undercarriage behind the wing exactly in the middle. Move the undercarriage forward and attach the mast to the proper hang point location on the wing keel. Consult the PO for the proper hang point for desired trim, speed, and loading at this time. Attach the backup cable at this time also. Figure 529. Lift up the nose and let the carriage roll backward until the wing is level and the control bar is in front of the front wheel of the carriage. Engage the parking brake and chock the back of the carriage wheels. Ensure everything in the F-light deck is free and clear so the wing can be lifted freely into position. Figure 530, lift the wing into position and lock the carriage mast. This position is unique to each manufacturer as some masts hinge above the F-light deck. Refer to the PO for details on a specific C aircraft. Figure 531, install the carriage front tube. Secure the control bar to the front tube with a bungee. Figure 532, attach any fairing or seats as required. Figure 533, an alternate method of setting up the wing is to do so on the ground. This is not preferable because the sail is susceptible to getting dirty. However, this method could be used for setting up wings if it is windy or if recommended by a particular manufacturer. The ground method steps are the same as those in the assembly procedure except after the control bar is assembled, the wing is rolled over so the control frame is under the wing. The wing is assembled as if it were standing on its control frame. After the wing is tensioned, the nose is lifted, the control frame pulled forward, and the nose wire secured. This is not a common practice, and the PO should be reviewed for details on this method if it is allowed by the manufacturer. Taking down the WSC aircraft, find a suitable area to take down the wing, preferably grass, cement, or pavement out of the wind. The best place is in a large hangar so no wind gusts can affect the takedown. If outside, align the wing perpendicular to the wind. It is important to note that during the takedown process, all protective pads must be put in the proper place so that no hardware can rub against the sail or frame during transport. The PO should specify what pads go where. Overall, pad everything along the wing keel plus the king post to prevent cosmetic and/or structural damage occurring during transport. Taking down a WSC aircraft is done in the reverse order of assembly with the following additional steps provided to get the wing neatly packed and organized into the bag. After the wing is detentioned and the battens have been removed from the wing, keep the right and left battens separate for easier sorting during the next assembly. Carefully bring the wings in towards the keel and pull the sail material out and over the top of the leading edges. Lower the king post and pad it top and bottom. This is also the time to pad the area underneath where the control frame is attached to the keel and where the wires are attached to the rear of the keel. Figure 534, bring the leading edges to the keel and keep the sail pulled out over the top of the leading edge, roll it up, and tuck the sail into the leading edge stiffener. Fasten around the leading edge with sail ties. Figure 535, it is best to take one sail tie and secure the two leading edges together so it fits into the bag. Figure 536, continue with the reverse order, bag on, flip wing over, and disassemble control frame at down tube and control bar junction. After the control frame is disassembled and laid flat along the wing as shown, the wires are not organized. Figure 537, pull the cables forward towards the nose and organize them so they are straight. Install the protective control frame pads and carefully zip up the bag while tucking everything in so there is no stress on the zipper. Figure 538. Wing tuning. Wings are designed to fly straight with a range of trim speeds determined by the manufacturer. If the wing does not fly straight or trim to the manufacturer's specifications, it must be tuned to fly properly. Any wing adjustment can change the handling and stability characteristics of the wing. Each wing is unique and the tuning procedures are unique for each wing. It is very important to follow the specific tuning procedures in the PO/AFM for the specific wing. The following are general guidelines to understand the tuning process. Tuning the wing to fly straight. Wings may turn to the right or left, depending on which way the propeller turns, at high power settings because of the turning effect described earlier in the aerodynamics section. If it does not fly straight for cruising flight, visually examine for any asymmetric right and left features on the wing before making any adjustments. Look for symmetry in the twist angle. Inspect the leading edge for any discontinuities, bumps, or an irregular leading edge stiffener. Ensure the pockets are zippered and symmetrical on both sides. Ensure the reflex lines are clear, straight, and routed properly. Check the battens to ensure the right and left match. Do not make any adjustments in the battens initially because reflex may have been added at the factory initially for tuning, and ensure the battens match the manufacturer's batten pattern. Check the batten tension on both sides and the leading edge tension to ensure it is symmetrical. If it is a used wing just acquired, research the history of the wing to see what might have happened which would cause it to not fly straight. For new wings, contact the manufacturer for advice. If these checks do not make the wing fly straight, then adjust the twist in the wing according to the manufacturer's instructions. More twist on one side decreases angle of attack, produces less lift, and will drop the wing, which makes it turn in the direction where more twist was added. For example, with an unwanted left-hand turn, either decrease the twist on the left-hand wing, increase angle of attack at the tip, or increase the twist on the right-hand wing, decrease the angle of attack at the tip. Batten tension is one way of fixing very mild turns. Increasing the batten tension at the tips especially decreases twist and raises the wing. For normal mild turns, most wings have an adjustment at the tip where you can rotate the wingtip around the leading edge. This is the easiest and most effective wing twist adjustment. Figure 539. For some models, reflex at the root can be adjusted on a side to adjust a significant turn. More reflex on a side means wing up, similar to reducing twist in a wing. As emphasized above, the PO for each manufacturer must be used for adjusting twist for wing tuning. Adjusting the tension on the leading edge is another method of adjusting the wing twist. However, different wings will react differently when tension is adjusted, so the PO must be followed for a particular wing. Some manufacturers do not suggest adjusting sail tension to adjust twist, but require equal tension with other adjustments to remedy an unwanted turn. For those wings utilizing asymmetrical sail tension to adjust twist, the following information is provided. Adjusting sail tension is most effective on slower wings with lots of twist. Adjusting sail tension affects some high-performance wings differently, making it necessary to consult the PO. However, on most wings, increasing sail tension at the tip increases leading edge flex, resulting in more twist. Tuning the wing to fly slower or faster. Most wings allow the hang point attachment to move forward to increase trim speed and back to decrease trim speed. If there is a situation where the hang point is at the most forward position and the wing trims below the manufacturer, recommended speed, or the trim speed is within 10 miles per hour, of the stall speed, an alternate method for increasing the trim speed is needed. For this situation, the twist must be reduced symmetrically to increase the angle of attack on the tips so they provide more lift and lower the nose for proper trim. This can be done by pulling back more on the crosstube tensioning cables, which reduces the twist in the wing. However, this procedure reduces the stability of the wing and decreases the handling ability of the wing because it is stiffer. This is a common adjustment for hang gliding wings for in-flight trim. However, this adjustment should only be made on WSC wings as specified in the PO for a specific wing. Raising and lowering the reflex lines affects airfoil reflex, and also changes the trim speed of the wing. Lower reflex lines speed the wing up and make it less stable, raising the reflex line slows the wing and make it more stable. Some manufacturers have this as an adjustable setting which can be varied during flight, other manufacturers have this adjustment where it can be made on the ground. Other manufacturers do not recommend this adjustment because it can lower the certified stability of the wing. Pre-flight inspection. Each aircraft must have a routine pre-flight inspection before flight. Use a written checklist during pre-flight and ground operations to maintain an established procedure. Figure 540, a written checklist is required so nothing is forgotten. Ground checklists include pre-flight preparation, pre-flight inspection, occupant pre-flight brief, flight deck management, startup, taxi, before takeoff, and an aircraft shutdown. Be smart and follow the regulations. Use a written checklist. All checklists should be secured so they do not fly out of the flight deck in flight and hit the propeller. Securing with zippered pockets and having lanyards for the checklists is recommended. Manufacturers of special light sport aircraft, SLSA, have checklists that come with the aircraft. Pilots with an experimental aircraft may need to develop their own. Certificates and documents. The FAA-RST step of pre-flight inspection is to ensure the aircraft is legally airworthy, which is determined in part by the following certificates and documents: airworthiness certificate, registration certificate, operating limitations, which may be in the form of an FAA-approved AFM/PO, placards, instrument markings, or any combination thereof. Weight and balance aero is the acronym commonly used to remember these items. The PIC is responsible for making sure the proper documentation is on board the aircraft when operated. Figure 541, aircraft logbooks are not required to be on board when it is operated. However, inspect the aircraft logbooks prior to flight to confirm the WSC aircraft has had all required inspections. The owner/operator must keep maintenance records for the airframe and power plant. At a minimum, there must be an annual condition inspection within the preceding 12 calendar months. In addition, the WSC aircraft may also need a 100-hour inspection in accordance with 14 CFR Part 91 if it is used for hire, for example, for training operations. Figure 542, If a transponder system is used, the transponder must be inspected within each preceding 24 calendar months. The pilot must have in his or her possession a sport pilot certificate for the aircraft being FL-ON, medical eligibility, and a government-issued photo identification. For a sport pilot certificate, medical eligibility can be a valid United States driver's license, which also serves as government-issued photo identification. To FLY the aircraft with private pilot privileges, the pilot needs a valid FAA minimum third-class medical certificate accompanied by a government-issued photo identification and private pilot certificate for WSC aircraft. See Chapter 1, Introduction to Weight Shift Control, for details on specific pilot certificates and privileges. Routine pre-flight inspection. The accomplishment of a safe flight begins with a careful and systematic routine pre-flight inspection to determine if the aircraft is in a condition for safe flight. The pre-flight inspection should be performed in accordance with a printed checklist provided by the manufacturer for the specific model of the aircraft. However, the following general areas are applicable to all WSC aircraft. The pre-flight inspection begins as soon as a pilot approaches the aircraft. Since the WSC aircraft can be transported by trailer, faa-h-8083-5 and foremost, look for any damage that may have occurred during takedown, loading, transit, unloading, and setup. Make note of the general appearance of the aircraft, looking for obvious discrepancies such as tires with low air pressure, structural distortion, wear points, and dripping fuel or oil leaks. All tie-downs, control locks, and shocks should be removed during the unloading process. The pilot must be thoroughly familiar with the locations and functions of the aircraft systems, switches, and controls. Use the pre-flight inspection as an orientation when operating a particular model for the faa-h-8083 time. The actual walk-around routine pre-flight inspection has been used for years from the smallest general aviation airplane to the largest commercial jet. The walk-around is thorough and systematic, and should be done the same way each time an aircraft is FL-ON. In addition to seeing the aircraft up close, it requires taking the appropriate action whenever a discrepancy is discovered. A WSC aircraft walk-around covers 4 main tasks: 1. Wing inspection. 2. Carriage inspection. 3. Power plant inspection. 4. Equipment check. Throughout the inspection, check for proper operation of systems, secure nuts/bolts/attachments/hardware, look for any signs of deterioration or deformation of any components/systems, such as dents, signs of excessive wear, bending, tears, or misalignment of any components and/or cracks. Each WSC aircraft should have a specific routine pre-flight inspection checklist, but the following can be used as an example and guideline. Wing inspection. Start with the nose. Inspect the nose plates and the attachment to the leading edges and keel. Ensure the nose plates are not cracked and the bolts are fastened securely. Check the wire attachments, top and bottom. Inspect the control frame, down tubes and control bar for dents and ensure they are straight. Inspect the control frame attachment to the keel. Inspect the control bar to down tube brackets and bolts. Figure 543, inspect fore and aft FL ying wire condition, attachment to the keel, and the lower control bar corner brackets. Inspect the left side FL ying wire attachment to the control bar bracket and condition of the FL ying wire up to the wing attachment. Examine the FL ying wire attachment to the leading edge and crossbar, as well as all hardware at this crossbar and leading edge junction. Figure 544, inspect the condition of the crossbar and the leading edge from the nose to the tip. Any discrepancies or tears in the leading edge fabric must lead to more detailed investigation of the leading edge spar itself. Inspect the tip area, including the washout strut and general condition of the tip. If it is a double surface wing, look inside the tip and examine the inside of the wing and its components. Figure 545, from the tip, inspect the surface condition of the fabric. Generally, if the fabric has not been exposed to sunlight for long periods and stored properly, the wing fabric should stay in good shape. Move along the trailing edge of the wing, inspecting the condition of the trailing edge and the tip batten attachments back to the keel. Figure 546, inspect the sail material, top and bottom, on the wing. Note that the trailing edge is vulnerable to rocks FL ying up from the wheels and hitting the propeller. Therefore, it is especially important to inspect the trailing edge in detail before each flight. At the aft keel area in the middle of wing, inspect the king post and all the condition of the wires from the king post to ensure they are not wrapped around the trailing edge battens. Figure 547, inspect the wing tensioning hardware where the crossbar tensioning cables attach to the rear of the keel. Repeat this same sequence for the right, or opposite, side of the wing, in the reverse order. Inspect the condition of the wing attachment to the carriage, including the backup cable. Figure 548, Carriage inspection. Inspect the mast from the top to the bottom and the carriage keel from the back to the front. Figure 549, check the front tube attachment and top and bottom security attachments. Check the seat security and seat attachments from the keel to the mast. Check the front nose wheel for proper play, tire inflation, and secure axle bolt. Test the ground steering bar and ensure there is smooth steering range of motion. Check the front shocks, if installed, the brakes for rust and corrosion, loose nuts/bolts, alignment cracks, signs of hydraulic fluid leakage, and hydraulic line security and abrasion, if so equipped. Figure 550, check the foot throttle for smooth operation and assure the parking brake is secured. Inspect the main landing gear drag struts, attachment to the keel, and attachment to the rear wheels. Examine the rear tires for proper inflation and tread plus the wheel attachment. Nut for security. Check main landing gear strut, landing gear shock absorber strut, and shock absorber operation. Figure 551, inspect all landing gear strut attachments to the airframe. Inspect the other side's rear landing gear by repeating the above procedure in reverse. Check all cowling for secure attachment and cracks. Figure 552, power plant inspection. Inspect engine attachment to the carriage for security and cracks. In addition to looking at the bolts and mounts, shake the propeller, as shown in Figure 553, to provide a secure check of the propeller, gearbox, engine, and engine attachment to the carriage. Fuel system, inspect fuel tank attachment and condition. Inspect fuel vent system, and ensure the fuel supply line is open. Some WSC aircraft have fuel shut-off valves outside the fuel tank. Inspect fuel pickup and fuel line running up to fuel filter. While inspecting all fuel lines, jiggle all fitings and connections to ensure they are secure. Inspect fuel filter and continue to follow fuel line up to fuel pump. Inspect the security and condition of fuel pump. Inspect fuel lines up to carburetors. Figure 554, induction system, inspect carburetors, including FLO bowl attachment and rubber bushing from carburetors into engine. Inspect fuel lines from FLO bowls to carburetor inlet. Inspect air inlet filter to ensure it is clean and secure. Figure 555. Ignition system, inspect ignition system wires to spark plugs. Inspect spark plug caps and wires to CDI units to ensure they are secure and fasten. Figure 556, ensure ignition switches are turned off. Cooling systems, ensure there is clear airflow for any cooling system, fan or radiator. Ensure no insects or birds created an obstruction to the airflow for the engine cooling system. Air-cooled, rotate the propeller and ensure that the cooling fan rotates also. Water-cooled, check the coolant level to ensure there is cooling fluid in the system. 4-stroke with additional oil coolers, ensure the oil cooler has clear airflow and that nothing is blocking it. Exhaust systems, inspect exhaust attachment to engine and EGT senders. Slightly jiggle the exhaust system to inspect the springs holding it together. All springs must be secure. Inspect the condition of exhaust system for cracks and attachment security. Figure 557, propeller gearbox, rotate the propeller in the proper direction only and inspect blades for cracks or nicks. Listen and feel for smooth operation and engine compression while rotating the propeller. Inspect propeller attachment to the gearbox and the gearbox attachment to the engine. Throttle system, check all throttle controls for smooth operation and proper travel and locking. Also check choke and or primer system for proper operation and travel. Flight deck inspection, the following should be performed for a flight deck inspection. Check seat security and proper adjustment for pilot and passenger. Check seat belt attachment and seat belt operation. Inspect the gauges for security and readability. Switch electrical master on and check gauges for expected readings. Figure 558, check ballistic parachute handle for security and proper location. Fuel overall, particular attention should be paid to the fuel quantity, type/grade, and quality. Modern WSC 2 and 4-stroke engines are designed to use autogas with various octane ratings as specified by the manufacturer for different models. If autogas is stored for more than 3 weeks, octane value may fall below the recommended rating. In this situation, it is best to drain the gas and use fresh gas. For engines designed for autogas, aviation gasoline, avgas, 100 LL can be mixed and used on a limited basis, but the lead in this is not good for the engine and additional precautions/procedures should be researched for the particular make/model of engine for primary use. Always use a higher grade/octane of fuel rather than a lower grade, or detonation will severely damage the engine in a very short period of time. Check the aircraft operation manual and the engine manual for the type of fuel to use. When attempting to fuel for maximum capacity, remember that many fuel tanks are very sensitive to attitude. Fill the aircraft on a level surface and check to ensure the amount of fuel in the tanks is adequate for the planned flight plus 30 minutes of reserve. Check the level in the fuel tank plus the panel-mounted gauge, if so equipped. To transport gasoline, clear gas cans are preferable because the fuel is visible through the container and allows a pilot to look at the container for fuel level. Figure 559, an important step in any pre-flight is to check for water and other sediment contamination. Avgas is more probable to have water in the fuel tanks because auto gas typically has alcohol in it to boost the octane. Alcohol absorbs water, running it harmlessly through the system. When using 100 ll avgas, water tends to accumulate in fuel tanks from condensation, particularly in partially filled tanks. Because water is heavier than fuel, it tends to collect in the low points of the fuel system. If avgas is used, drain any water from the low point in the system. Oil of 4-stroke engines oil levels should be checked during each pre-flight and rechecked with each refueling. 4-stroke engines can be expected to consume a small amount of oil during normal operation. If consumption grows or suddenly changes, qualified maintenance personnel should investigate. If the Rotax 912 oil level is low when the oil is checked, rotate the propeller in the correct direction, counterclockwise, facing it, to pump any oil from the engine back into the oil tank for a proper measurement and recheck oil level before adding oil. Figure 560, check the reservoir level of 2-stroke engines with oil injection at each gas fill up. It is also very important to ensure the oil reservoir has clear air vent holes to allow continuous flow of oil to lubricate the engine. Always use the same type of oil because different types of oil harden and stop the oil injection process, resulting in a seized engine. Additionally, check to see if the oil injection system lines from the tank to the carburetors are clean and secure. Some 2-stroke engines have a separate lubrication system for the inlet rotary valve. This system should be checked for proper level and leaks. Figure 561, when adding fuel and oil, ensure that the caps has been securely replaced. Ready aircraft to enter flight deck either before or after the routine pre-flight inspection. The aircraft should be unsecured, positioned for starting, and ready to enter the flight deck. A checklist provides the basic steps. Untie aircraft, secure tied down ropes in aircraft, or coil neatly if they stay at airport. Remove ground chocks and secure in aircraft. Locate a suitable area to start engine that is free of dirt and has minimal dust, preferably a paved or grassy area away from people and objects. Position aircraft so prop blast is clear, verify that brakes are on, throttle is closed, and propeller area is cleared. Position into wind, if possible, for best cooling during warm-up. Occupant pre-flight brief or pre-flight brief ENG is required to ensure the passenger is informed on the proper use of safety equipment and exit information. This can be done before entering the aircraft, and must be accomplished before starting the engine. Manufacturers of SLSA aircraft typically have printed briefing cards that should be used. The following is a comprehensive checklist that can be used as a guideline for any pre-flight brief ENG. Seat belt fasten and unfasten procedures. Seat belts must be worn for takeoff and landing, and should always be worn during flight. What passengers can hold on to and what not to touch. Positive exchange of controls using a 3-step process. You take the controls, I have the controls, you have the controls. Look for other ground and air Trafฟี่. Flight deck entrance and exit procedures including emergency exit. Ballistic parachute operation procedures. Engine out situation and procedures for planned flight with diversions. Hand signals in case electric loads must be shut off or internal aircraft communications not functioning. Water landings with engine out situation, if planned flight over water. Ensure nothing can fall out of pockets while in flight. This is especially important since the propeller is in back. Helmet fastening and unfastening procedure. Figure 562, review the type of aircraft, special or experimental, which is not an FAA certified standard category aircraft. Fire extinguisher operation, if so equipped. All safety systems, as required. Use restroom before entering aircraft. Flight deck management after entering the flight deck. The pilot should first ensure that all necessary equipment, documents, checklists, and navigation charts appropriate for the flight are on board. Figure 563, if a portable intercom, headsets, or a handheld global positioning system, GPS, is used, the pilot is responsible for ensuring that the routing of wires and cables does not interfere with the motion or the operation of any control. Regardless of what materials are to be used, they should be neatly arranged and organized in a manner that makes them readily available. The flight deck should be checked for articles that might be tossed about if turbulence is encountered, and any loose items properly secured. When the pilot is comfortably seated, the safety belt and shoulder harness, if installed, should be fastened and adjusted to a comfortably snug fit. The safety belt must be worn at all times the pilot is seated at the controls. Checklist after entering flight deck, seats adjusted for full operation of all controls. Seats locked into position. Put on seat belts, lap faa-h-80, then shoulder, and adjust so all controls and systems can be fully operated. Check all control systems for proper operation. Check all systems operations. Demonstrate and practice flight and emergency equipment and procedures. Demonstrate and practice what passengers can hold on to, and what not to touch. Demonstrate and practice positive exchange of controls. Remove safety pin for ballistic chute operation. Install helmet, if applicable, and headphones. Check intercom and radio communication systems. Install eye protection, safety glasses, helmet shields. It is important that a pilot operates an aircraft safely on the ground. This includes being familiar with standard hand signals that are used universally for ground operations. Figure 564, Engine start. The specific procedures for engine start vary greatly since there are as many different methods as there are engines, fuel systems, and starting conditions. The engine start checklist procedures in the PO should be followed. The following are some basic steps that apply to most aircraft. Key in, ignition on, master power on, check gauges for operation and fuel level. Fuel pump on, or pump fuel bulb to faa-ll carburetor bowls, system switches on. Some WSC have specific system switches turned on after the engine is started because engine starting may create lower voltage, possibly damaging instruments or systems. If in doubt, start engine and then turn on instruments and systems not needed for starting. Both ignition system switches on, choke/enrichen are on, or pump primaire is appropriate, throttle closed, brakes on, ensure propeller area is cleared, loudly announce to propeller area clear prop, and wait for any response. Start engine through pull cord start or electric start. Do not try to hand prop under any circumstances. Ensure the aircraft does not move, keeping hands on ignition switches for quick shutdown, if necessary. Adjust throttle, choke or enrichener to keep engine running smoothly. Turn on electric instruments if applicable. Check gauges for proper ranges, oil pressure, revolutions per minute, RPM, charging voltage, engine temperatures within ranges, etc. Continue to monitor area and shut down engine if any person or animal approaches. A relatively low RPM setting is recommended immediately following engine start. This is typically a slight increase in the throttle to keep the engine running smoothly. It is not recommended to allow the RPM to race immediately after a start with a cold engine, as there is insufficient lubrication until the oil pressure rises on 4-stroke engines, and unequal heating on 2-stroke engines. In freezing temperatures, the engine is also exposed to potential mechanical distress until it warms and normal internal operating clearances are reached. On 4-stroke engines, as soon as the engine is started, the oil pressure should be checked. If it does not rise to the manufacturer's specified value, the engine may not be receiving proper lubrication and should be shut down immediately to prevent serious damage. Taxiing. Since an aircraft is moved under its own power between the startup area and the runway, the pilot must thoroughly understand it and be proficient in taxi procedures. When the brakes are faa-h-80 released and the aircraft starts to roll, the brakes should be tested immediately for proper operation. Applying power to start the WSC aircraft moving forward slowly, then retarding the throttle and simultaneously applying pressure smoothly on the brake may be needed to accomplish this. If braking action is unsatisfactory, the engine should be shut down immediately. When yellow taxiway centerline stripes are provided, they should be followed unless it becomes necessary to deviate to clear aircraft or obstructions. Figure 565, an awareness of other aircraft that are taking off, landing, or taxiing, and consideration for the right-of-way of others is essential to safety. When taxiing, the pilot's eyes should be looking outside the aircraft, to the sides, as well as the front. The pilot must be aware of the entire area around the aircraft to ensure that it clears all obstructions, people, animals, and other aircraft. If at any time there is doubt about the clearance from an object, the pilot should stop the aircraft and check the clearance. The WSC aircraft does have the advantage of the wingtip capability of being raised and lowered to clear objects. It is difficult to set any rule for a single, safe taxiing speed. What is reasonable and prudent under some conditions may be hazardous under others. The primary requirements for safe taxiing are positive control, the ability to recognize potential hazards in time to avoid them, and the ability to stop or turn where and when desired without undue reliance on the brakes. Pilots should proceed at a cautious speed on congested or busy ramps. Normally, the speed should be at the rate at which movement of the aircraft is dependent on the throttle. That is, the speed should be low enough that when the throttle is closed, the aircraft can be stopped promptly. A GPS provides this speed since the airspeed indicator is not effective at these lower speeds. A rule of thumb is 5 miles per hour, brisk walking speed, or 10 miles per hour for long unobstructed areas. When taxiing, it is best to slow down before attempting a turn. WSC aircraft taxi with the wing typically held in a neutral position, but stronger winds may require positioning of the wing so it cannot be lifted. Position controls properly for wind conditions. Strong tailwind, pitch control normal or slight nose up with wings level. Strong headwind, pitch control nose down with wings level. Strong quartering tailwind, nose normal with upwind wing slightly down so wind cannot catch it, but not too low to cause excess stress on carriage mast. Strong quartering headwind, nose down with upwind wing slightly down so wind cannot catch it, but not low enough to cause excess stress on carriage mast. Checklist for taxi plan: taxi path to runway to avoid paths that would put the aircraft behind any propeller or jet blast. Observe other aircraft closely which could start up and taxi in front, if practical. Turn on strobe light if applicable. Release brake. When faa-h-8083-5 rolling, immediately check brakes, steering, and shut down if either is not functioning properly. Observe proper right-of-way while taxiing. Taxiing aircraft yield to landing aircraft, so landing craft have right-of-way over taxiing aircraft. 2 aircraft approaching head-on will turn right, similar to what is done in a car. 2 aircraft traveling in same direction, the forward aircraft has right-of-way because its pilot cannot normally see the aircraft in back. With 2 airplanes converging, the pilot who sees an aircraft on the right must avoid that aircraft. The aircraft on the right has the right-of-way. Runway incursions: observe all taxiway and runway markings. Runway incursions are a signify can't risk and must be avoided. This is a most important concept. Taxi slowly and observe the basic airport markings/signs. Clearance to proceed must be obtained prior to taxiing across any runway or entering a runway to take off. There could be large aircraft, which may not be able to respond to WSC aircraft quick movements. An important runway marker is the hold short line. Always stop before reaching this line and get clearance before crossing it. Figure 566, at a towered airport, this is clearance from the tower. Always read back tower instructions clearance when received from tower before proceeding. At a non-towered airport, the clearance procedure is to listen to and monitor all air Traffic on the airport radio frequency. Observe all air Traffic taxiing and in the pattern. After listening on the radio and observing all possible Traffic, announce position and intentions before crossing runway or entering runway. If crossing runway, announce once you have taxied across that you are clear of runway. Before takeoff check: the before takeoff check is the systematic procedure for making a check of the engine, controls, systems, instruments, and avionics prior to flight. Normally, it is performed after taxiing to a position near the takeoff end of the runway. Taxiing to that position usually allows sufficient time for the engine to warm up to at least minimum operating temperatures. This ensures adequate lubrication and internal engine clearances before being operated at high power settings. Many engines require that the oil temperature or engine temperature reach a minimum value, as stated in the AFM/PO, before high power is applied. Some WSC aircraft are ram air-cooled, where the cooling air must be rammed into the cooling radiator during flight. On the ground, however, little or no air is forced through the radiator. Prolonged ground operations may cause engine overheating. Some designs place the cooling radiators near the propeller so the propeller produces reasonable airflow to cool the engine. Air-cooled 2-stroke engine aircraft may have an integral engine-driven cooling fan and can idle indefinitely without overheating. Monitoring engine temperature to be within limits is important for aircraft operations on the ground. After taxiing to the runway entrance run-up area and before beginning the pre-takeoff check, the aircraft should be positioned clear of other aircraft. When you taxi out to the run-up area, position yourself where other aircraft can easily taxi to a suitable run-up area. There should not be anything behind the aircraft that might be damaged by the prop blast. To minimize overheating during engine run-up, it is recommended that the aircraft be headed as nearly as possible into the wind. After an aircraft is properly positioned for the run-up, the nose wheel should be pointed straight. During the engine run-up, the surface under the WSC aircraft should be FIRM, a smooth, paved, or turf surface, if possible, and free of debris. Otherwise, the propeller may pick up pebbles, dirt, or other loose objects and hurl them backward or into the sail. Figure 567, While performing the engine run-up, the pilot must divide attention inside to look at the instruments and outside the aircraft to look for other Traffi. If the parking brake slips, or if application of the brakes is inadequate for the amount of power applied, the aircraft could move forward unnoticed if attention is crossed only inside the aircraft. Each aircraft has different features and equipment, and the before takeoff checklist provided by the WSC manufacturer should be used to perform the run-up. Here is a general checklist. Verify the strobe light is on, if applicable. Trim is set to proper speed for takeoff. Brakes are set. Ignition check. Always divide attention into and out of the FLIght deck in case the brakes cannot hold the aircraft still at the higher power settings. Some ignition checks are done at idle. See PO for engine specify CS. If the brakes start to slip and the aircraft starts moving, decrease power immediately and re-evaluate how to run up and keep the aircraft stationary during run-up. Run up engine to consistent RPM higher than idle. Switch from both ignition systems to one and watch for a slight drop in RPM. Do the same for the other ignition system. Verify engine temperatures, EGT, CHT, oil and/or water, and oil pressure are within the acceptable ranges. At towered airports, obtain clearance from tower when ready for takeoff. At non-towered airports, when all air traffic is clear from observations and radio communications, and while holding short before the runway boundary, hold short, line, announce the aircraft is entering the runway. This is a pilot's clearance at a self-announce airport to enter the runway. At all airports, do a visual verify cation that there are no aircraft landing before entering the runway. After landing, during the after-landing roll, the WSC aircraft should be gradually slowed to normal taxi speed before turning off the landing runway. Any significant degree of turn at faster speeds could result in the WSC aircraft tipping over and subsequent damage. Figure 568. To give full attention to controlling the WSC aircraft during the landing roll, the after-landing check should be performed only after the aircraft is brought to a complete stop clear of the active runway. Post-flight, parking, and securing a FLIght is never complete until the engine is shut down and the WSC aircraft is secured. A pilot should consider this an essential part of any FLIght. Unless parking in a designated, supervised area, the pilot should select a location which prevents propeller or jet blast of other airplanes from striking the WSC aircraft. The pilot should always use the procedures in the manufacturer's checklist for shutting down the engine and securing the airplane. Some of the important items include: set the parking brakes on, set throttle to idle and let engine cool down to manufacturer's specifications, turn ignition switch off, turn electrical units and radios off, turn master electrical switch to off. After engine shutdown and exiting the aircraft, the pilot should accomplish a post-flight inspection. When the FLIght is complete, the aircraft should be hangared or tied down appropriately for the situation. There are a number of ways to park and secure the WSC aircraft depending on the situation. With normal aircraft tie downs, little to no wind, and a short time frame for unsupervised parking, the WSC aircraft can be secured by tying both leading edge crossbar junctions to the typical airport wing ties. The control bar is secured to the front tube with a bungee cord to stabilize the nose, or the control bar can be pulled back and attached to the seat rail to keep the nose down in case of a possible headwind. Figure 569, if higher winds are present, the WSC aircraft can be positioned so the wind is blowing from the side and the wing tip is lowered on the windward side so the wind is pushing down on the wing. This can be used to exit the aircraft and tie the wing down in higher winds. Figures 5-70 through 5-72. For overnight or higher wind tie down, the complete wing can be lowered to the ground with a 4-point tie down. Each wing at the crossbar/leading edge junction plus the nose and rear of the keel can be tied down for greater resistance to wind. For humid or dusty areas, a cover is recommended for the carriage to cover the engine and FLIght deck. Figure 573, the best way to secure the WSC aircraft for overnight is to put it in a hangar. If it must be stored outside, remove the wing and fold it up so there is no chance of the wing being damaged in an unforeseen gust front. Chapter summary: pre-flight preparation should include the overall evaluation of the pilot, experience, sleep, food and water, drugs or medications, stress, illness and overall aeronautical factors, as discussed in Chapter 1, Introduction to Weight Shift Control. Aircraft, proper transport, fuel, weight, does not exceed maximum, aero, takeoff and landing requirements, equipment. Environment, where to fly, weather conditions, forecast for departure and destination airfields, route of FLIght, and specify airport pattern/runway lengths. Pilot capabilities must be compared to the weather limitations for the decision of whether to go to the airfield. External pressures, schedules, available alternatives, purpose of flight. Preflight procedures include setup of the wing and mounting the wing on the carriage, if trailered or taken down. Tuning the wing to FLY straight and at the proper trim speed. Preflight inspection with written checklist of wing, carriage, power plant systems, and flight deck. Readying aircraft to enter by proper positioning and occupant preflight brief. Engine start, taxi, and performing before takeoff check. Post-flight procedures include taxi off runway to appropriate location. Park exit, post-flight and documenting any discrepancies. Hangar, secure or take down.